Hello, hello, it's Mrs. Edwards and we're back. It is time to do math and I love it. No, seriously, I love logarithms and I'm super excited to share this lesson with you. And I hope that you love logarithms as much as I do when we finish this chapter. So the first couple of properties that we're going to go over, they remind me a lot of that memory matching game that you played as a kid. You have all those cards face down and you're looking for a match. We got a moon, match, and we toss them out. And we have an apple, a match, and we toss them out. And then as soon as we get a match, right, they disappear. So the first couple log problems are like that. When we get matching bases, everything goes away. I just had to leave these pictures in here. This is the Beaver Gang card game. Oh my goodness, I know, a little bit weird, but apparently it's a story of a couple of beavers, one shaved beaver who uses Old Spice and has just taken a shower, and then another beaver that's a stinky hairy one. I don't know, but it is a card matching game for kids, supposedly. All right, well, let's take a look at those first couple properties. All right, first let's read this logarithm. We read this log base b of b to the x. Log base b of b to the x. So notice base b, this is how we read a logarithm, it's base. And then if I had 2 to the third power, the 2 is the base and the 3 is the exponent. So this is the base of the log and this is the base of the power. And when those bases match, poof, those go away and all we have left is x. Okay, similarly over here on the right, this b is in the base and then all of this is up in the exponent. So up in the exponent is log base b of x. So b is the base to the power of log base b. So since those match, poof, matching game, those go away and all we have is x. Okay, then let's move on to just some invisible bases. If you do not see a base number, every logarithm has a base. And if you don't see the base number, well then it has to be 10. It's kind of like if you had the square root of a number, you know the little index number on a square root is 2 when you don't see it. But if you wanted it to be something else like cube root, fourth root, fifth root, you'd have to actually write in the little number. Mathematicians, darn it, we are kind of lazy writers. So that's what's going on here. If you do not see a base, then guaranteed it is 10. Now, we've already used well, if I just leave it off, I'll know it's a 10. So we can't just leave it off, but there's another base number that is extremely common, and that is base E. And when you read this one, it's natural log, ln stands for natural log of A, and we don't see the base number, but every single time you have a natural log, the base is E. Now, E is not a variable, right? It's like pi, an irrational number. It's a number that goes forever without a pattern, happens to be about 2.71. So we have natural log base E of A. You will never, ever have a base other than E that goes with natural log. It's kind of like using circumference. If I said, find the circumference of the rectangle, you'd be like, Edwards, what are you talking about? You know what you mean, circle? Oh, yeah. So it's E only goes with natural log, kind of like circumference only goes with circles. All right. So next thing we're going to do is ultimately to use these two properties up here, getting those bases to match, we've got to be able to rewrite things so that the base number really stands out to get the bases to match. So we're going to do this in a little bit of a progression, starting with making the base in a power, right? A power is 2 to the third power, 2 is the base, 3 is the exponent, all of it is called a power. We're going to rewrite these powers to make the bases really stand out. So let's give that a try. All right, so we want to rewrite this so that we have the base really standing out in exponential form. There's a lot that's invisible here, right? The 5 is really to the first power, and then we don't see the little index number, so we know it has to be a square root. When you go over to exponential form, the fraction is inside out, kind of like you turn a shirt inside out. Inside, exponent 1, out 2. So if I do inside over out, we get 5 to the power of 1/2. And we've rewritten this where we have that single base raised to an exponent. Okay, how about this one? First thing we want to do is get rid of that root symbol. And we're going to do that the same way we did the square root of 5. So in the denominator, we're going to have e to the power of inside out, e to the power of 1/2. Now I want a single base, one number to a power. So I need to get this e to the 1/2 moved to the numerator. So if we cross the line, we change the sign of the exponent, the fraction bar line. So I'm going to take e to the 1/2, cross the line, put it up there in the numerator, and to do that, I will change the sign of the exponent. So that ends up being e to the power of negative 1/2. So e is our base, exponent negative 1/2. Okay, how about this one? The 9, yes, the 9 is 9 to the first power. But you want to be on the lookout for perfect squares, perfect cubes. So 9 is also 3 to the second power, right? So if 9 is 3 to the second power, and then I do inside out, right, that 3 will be to the 2 over 4, all of a sudden that fraction simplifies. 2/4 is 1/2. And now we can move the 3 to the 1/2 to the numerator. If we cross that fraction bar line, we're going to change the sign of the exponent, and we have 3 to the power of negative 1/2. All right, so be on the lookout there. If the 9, say the 9 was 27, I would want to write it as 3 to the third power. Okay, so let's keep going here. We'd like matching bases. It's the only way we're going to get this all smushed together. So 9 and 27. 9 is 3 times 3. And 27 is 3 times 3 times 3. So let's replace the 9 with 3 to the second power, the 27 with 3 to the third power. Okay, and then we want to simplify the numerator and denominator. We have a power raised to a power. Power to a power, multiply. All right, so when you have a power raised to a power, you multiply exponents. So I'm going to have 2 times 13 and 3 times 8. Right, now you can envision in the numerator 3 times 3 times 3 times 3 times 3, and we have a string of 26 times 3s. And then on the bottom, 3 times 3 times 3 times 3 times 3, all those 3s in the bottom. We can start canceling those off. We're going to have more 3s in the numerator than we are the denominator. How many extras are we going to have in the numerator? We're going to have 2 extras. That's where that rule comes in. When we have like bases, we're going to subtract exponents, and we have more of them in the numerator. So I'm going to have to the power of positive 2. I could simplify and call that 9, but let's look at the directions. Rewrite as a single base raised to a rational number exponent. Okay, so our exponent, we've got 2. If you said 9 to the first power, I suppose we could call that good because you would have a base and a rational exponent. But I'm going to leave that as 3 to the second. Okay, now that we have this idea of rewriting to really emphasize a single number to a power, we can use those log properties efficiently. If we want to simplify this logarithm, every logarithm has a base. So remember, if it's invisible, this must be base 10. The only way to simplify here is to get the bases to match. Now I do see a 10 there, but that's not a base. We need a number to a power. So we're thinking, how can I rewrite 1 over 10? Okay, well, this 10 is to the first power. So if I cross that fraction bar line, I'll change the sign on the exponent, and that's 10 to the negative 1. Now we've got those matching bases. And then when we get a match, boom, they're gone. So our answer is negative 1. All right, let's take a look here. Now, natural log, we don't see a base, but we know every single time we have a natural log, the only base it could be is e. Rewriting this so that we can get a match, we've got to have this be e to the power, and we know that, right, because the e right there. So the e in the denominator was, so we had square root of e, so that's e to the 1/2, moving that to the numerator, e to the negative 1/2. And look at there, we have those matching bases. And when we get a match, boom, they're gone. Answer, negative 1/2. Okay, so here, this one looks a little tricky, but there's kind of a giveaway, because see how the base is 3? The only way we're going to be able to simplify is if we can write what's inside parentheses as 3 to the power of something to get those bases to match. So thinking about 9, right, was 3 to the second power, and then 3 to the second would be 3 to the 2 over 4, and then when we cross that line, and we just did this a minute ago, so I'm kind of doing these fast, but 3 to the 2/4 is 3 to the 1/2, cross that fraction bar line, those 3's match, and boom, we get negative 1/2. All right, one more here. The giveaway of what we want to accomplish is the base number on the log is 3. So if the base number is 3, what's inside parentheses needs to be written as 3 to a power. So we're looking at 9 and 27, and that was kind of a hint that we want a 3. That 9, remember, was 3 squared, 27 was 3 cubed, power to a power, multiply. So we have 3 to the 26th over 3 to the 24th, and then subtract exponents, and boom, there's a match. Ah, kids play, right? You got this. Couple more, the other matching bases. So e right here is the base. Natural log of 7 is up in the exponent, but e is the base, and then we're like, well, what's the base on natural log? The only base that it could be is e. So notice we have those matching bases again. And once we get a matching base, all of that's gone, and we get 7. Okay, how about that one? One more time, every single logarithm has a base. We just don't see it. So the base right there, if it's log and we don't see it, we know that's a 10. So we have 10 as the base, and up in the exponent is log base 10 of 0.4. So we have these matching bases. Christmas is coming. I feel like these are blinking Christmas lights. Okay, and a match, so they go away, and we have 0.4. Not much to do here. We just notice base 3 and base 3. So if we have matching bases, all that goes away, and we get just 5. All right, so far we've gone over 2 properties, both of them having to do with matching bases. We have just one more property, and that is going from logarithm form to exponential form. So here we have logarithm form, and let me go ahead and read that for you. Log base b of y is x. So this is my base. We're going to go to exponential form, and it shouldn't surprise you if you're going to go to exponential form, the vocabulary matches. So log base b. So if that's a base, then when we go to exponential form, right, that's the base. Those match up there. Okay, the other big picture, I just can't believe how many people study logarithms and they get so caught up in memorizing rules, and they're like, what is it all for? The purpose, the main purpose, there are more purposes, but the main purpose of a logarithm is to solve for a variable that's stuck up in the exponent. Okay, you can't undo the order of operations to isolate the variable if the variable is up in the exponent. Every time you see a variable up in the exponent, that's the giveaway that, to solve this equation, I'm going to need a logarithm. So if you know that the answer to all logarithms are really just exponents, because that's what they find, then you look at these forms and you're like, oh, a logarithm equals x, but all logarithms are exponents, so this x is the exponent, and then by default, there's the y. Okay, that's understanding the pieces, but here's a silly story for you. We're going to be really literal for a second with a story that I made. So we have log, here's a log, log. All right, then base, that's a beaver in case you can't tell what my drawing is. All right, so log base beaver of y is, now if you use your imagination here, this equal sign is like the water, equals x. All right, so log base is the beaver of y equals is the water, x. All right, now, this is a little bit silly, but the beavers do what they do, right? They're going to tunnel and they're going to make dams. All right, so here's this beaver. He tunnels under. He comes up on the other side. And when he comes up, there was an X and he was digging underneath there. So he pushed that X up. And then over here, there was a tunnel, right? He dug underneath. So that log fell in. And what do you know? We are to exponential form. So I'm going to do that one more time. Okay, beaver, he tunnels under. He comes up on the other side and pushes up what's already there. So it's pushing that up. So it's b to the x. And then that log falls in the hole that he just created, so we don't see it anymore. And we have now changed to exponential form. So let's put that in action. Let's say that I want to change this to exponential form. So with my silly story, okay, we have log. In this case, the base, the beaver, is the number 2 of x equals 3. If we want to go to exponential form, the beaver, he's got a tunnel. So beaver's tunneling under, comes up on the other side, pushes that 3 up. And so we're going to have the base, which was 2 raised to the third power, and then that log falls in the hole. All right, so we have x equals 2 to the third, which is 8. All right, one really big takeaway before we do just one last problem like this. Solving equations that have a logarithm in them. It comes down to one of two things. There's like a million ways the original can look, but it will only come down to two things. You are going to either have a single log on one side of the equal sign equal to something else, and as soon as you get it to look like that, the beaver's going to tunnel. and that's going to solve the problem. The other way that you solve logarithms is to get one log on one side and one log on the other, and then you can drop your logs off. But they all boil down to that. So this idea of once we get it to look like a single log, the beaver tunnels, and that solves it. All right, so one more. We don't see the base, but every logarithm has a base. So we have log. What is the base that we don't see? That should be log base 10 of x equals -2. Right, so I just rewrote it there. Equals -2. So the beaver in this case, that's like the number 10. So the 10 is going to tunnel under and come up on the other side, and the log falls in the hole. Okay, the 10 is tunneling under, coming up underneath that -2, pushing that up, and then the log falls in the hole that the beaver just created. So that means we're going to have x equals 10 to the -2, which of course is 1 over 10 squared, which is then 1 over 100. All right, so 3 main properties today. 2 of them are really about just matching the bases, and once you get a match, it disappears. And then changing from logarithm form to exponential form, and you can think, just let the beaver tunnel under, and you will have changed to exponential form. Okay, I hope that you're starting to love logs.